Section 3.9, Differentials. The symbols dy and dx that appear in the derivative dy dx are called differentials. Now let's think about what these things are going to mean. We're going to start with what do delta y and delta x mean. So if y equals f of x and f is differentiable at x, then we know here's my x, here is, this length is delta x, here is delta y. So on my function, I have my point x, f at x, and I'm going to go delta x this way and delta y this way. So the x coordinate here is x plus delta x, and the y coordinate is f at x plus delta x. So my change in y, delta y, is f at x plus delta x minus f at x. That makes sense. This y coordinate minus that y coordinate. Now dy dx we know is f prime of x, but dy could be written as f prime of x dx. So what do I know about these things? We know that delta y is my change in y on f of x. So what are dy and dx? Let's look at this picture again in a little bit different way. Once again, here's my curve. And notice that when I go from here to here, my change in x, that's what that length is. And here's my change in y, but these are on the tangent line. So notice dx is delta x. In other words, the change in x on the tangent line is equal to the change in x on the curve. Conclusion: dy is the change in y on the tangent line. Now, an equation of the tangent line at our curve at the point A, f at A, would be, from our slope formula, we know slope formula is y minus y1 equals m times x minus x1. So using this notation, it is y minus f at A equals f prime at A, the slope at A, times x minus a. And I can use this equation to approximate a value for y on the function found by f at A, just adding this over, plus, so where I am at A, plus the slope times x minus a. Also, let us remember dy is f prime of x dx because of this relationship. Therefore, the linear approximation of this function is f at x, which is approximated by f prime at a times x minus a plus f at a. The linear approximation is the use of the tangent line to approximate y values of the function. This is a very important concept in this course. Example, y equals x squared. Find dy when x is 3 and dx is 4. Well, first of all, dy dx is 2x. So let's write this in differential form. Dy is 2x times dx. Well, we know when x is 3, at the instant when x is 3, it is changing by 4 units. So dy dx is 6 times dx. Translation: as we travel along the tangent to the curve, y equals x squared, at x equals 3, then a change of dx units produces a change of 6 times that in our y. Therefore, dy is 24 units. So when x is 3, if I change x by 4 units, y is going to change by 24 units. So at the point where x is 3, if I change x by 3 units, y is going to change by 24 units. We are going to compare delta y and dy. Let us remember dy dx is f prime of x. We know that. Let's let y equal f of x, which is 1 minus 2x squared. So delta y is going to be f of x plus delta x minus f at x. dy is going to be f prime of x dx. So let's first of all work with delta y. Now we know our x is 0, okay? Our change in x is going to be negative 0.1. And so substituting into this, I have delta y to be f of 0 plus the change in x, negative 0.1, minus f at x, which is 0. Now we're going to do that work. 0 plus negative 0.1 is negative 0.1. So I need f at negative 0.1, and I want to subtract f at 0. Now f at negative 0.1, we're going to substitute that in for x right there. So we have 1 minus 2 times negative 0.1 quantity squared minus 1 minus 2 times 0 squared. Now, negative 0.1 squared is positive 0.01. So I have 1 minus 2 times 0.01 minus 1 plus 0. That gives me, the ones drop out, negative 2 times 0.01, which means delta y is negative 0.02, or 2/100ths. What does that mean? That means when I decrease my x-coordinate by 1/10, my y-coordinate on the function is decreased by 2/100ths. So when I decrease my x by 1/10, my y is going to get decreased by 2/100ths. That is on the function. Let's look what happens on our tangent line. So dy is equal to f prime of x dx. So f prime of x is negative 4x, okay? And the change in y going to be approximated by the slope times the change in x. F prime at 0 is going to be 0. Dx is the same as delta x, negative 0.1, so 0. So what is going to happen here is we're going to have no change in y on the tangent line. Well, why is that? If you think about this function, this is negative 2x squared, so the parabola is going down, and we're shifted up 1 unit. What is happening at 0? Well, at 0, we have a horizontal tangent line. So how is my y value changing on the tangent line? Not at all in this problem, because my tangent line is horizontal. But on the function, my y value is going down by 2/100ths. Find the differential form of y equals x minus 1 over x plus 1. That's pretty easy. We're just going to use our quotient rule to find the derivative. Do a little bit of algebra. So dy dx equals this, 2 over x plus 1, the quantity squared. And differential form is simply dy equals 2 over x plus 1, quantity squared, dx. This form is going to be really important when we start chapter 4 in the next lecture manual, which you are picking up next week. All right, let's do a little more. The measurement of the radius of the end of a log is found to be 14 inches, with a possible error of 1/4 of an inch. Use differentials to approximate the possible error in computing the area of the end of the log. So how far off are we on that area of the end of the log? Why would we want to know that? I don't know. Maybe we're making a table out of the log. Who knows? All right. So A is pi r squared because the end of the log is ideally a circle. So we know dA dr is 2 pi r. My r is 14. Delta r is the same as dr, which is the error of 1/4 of an inch. So plus or minus 1/4. This is in inches, so 1/4 of an inch. That would be correct. And my change in my area is going to be approximated by dA, which is 2 pi r dr. Substitute what we know. 2 pi r dr is plus or minus 1/4. That gives us 28 pi plus or minus 1/4, which of course gives us plus or minus 7 pi square inches. And when we take 7 and multiply it by pi, we get plus or minus 21.991 square inches, or about 22 square inches. Now, error in the linear approximation is always written like this. It's called propagated error, plus or minus the change in y, delta y. And what you should know is that error is always expressed as a positive quantity. So if we say the error is 1 inch, we mean plus or minus in our calculations. It could go up or down. The error in a calculated value of a function y is delta y, which can be approximated by the differential dy. Now, a better idea of error is given by what is called relative error, which is found by comparing the propagated error with the function. From above, the relative error would be the propagated error compared to the actual area. And we're going to approximate it by dA over A. Now, dA was 2 pi r dr. A is pi r squared. You can see the pi and one of the r's canceled. So I get dA, the relationship of dA to A is 2 dr over r. So what does that mean? That means the relative error for the example above involving area is about 2 times the relative error in the radius. One more time. The relative error for the example above involving area is about 2 times the relative error in the radius. So the relative error in the radius in our example, dr over r, and remember our change in radius was 1/4, so we can make this 0.25 over r, which is going to give us this nice decimal. Why do I like that? Because now we can start talking about percentages. It produces a relative error of about, again, twice that, 0.03571 in the area. The errors could also be expressed as percentage errors of 1.79% in the radius and 3.57% in the area. Kind of a nice way to think about all this. Your TPs are 3, 5, and 15. See you next time.